Yeah, ladies and gentlemen, it's a great pleasure for me to welcome you on this webinar tonight. It's again Wednesday afternoon, 7 o'clock in the evening. And tonight we will again tackle the question about hydrogen ship transport. Yeah. And from this, it's a great pleasure for me to welcome you first, all of you, on behalf of the organizer, which is on the Tunisian side at GIZ in Tunisia. It's the University of Carthago, and it's the Green Hydrogen Society in Tunisia. On the German side, it's Hamburg University of Technology, together with the VDI here in Hamburg, as well as the Energy Research Association here. So, and as last weeks, we are moving slowly but surely through the overall provision chain. And one question, one challenge, what we still have to tackle and where the blueprint is not fully available yet is, of course, the transportation of the hydrogen via ship or via long distances. I mean, last week we've heard about the hydrogen backbone with the pipelines or with the, let's say, gas network. So this is one option, but if you would like to transport them on a longer distance, then we discussed about liquid hydrogen transportation, but there we understood that this is quite demanding from a technology point of view, as well as from a, let's say, energy point of view. And we are still a little bit at the beginning of liquid hydrogen transport. Therefore, there's still the question open, do we have alternatives? Do we have possibilities how to transport hydrogen in a more smart, in a more intelligent, also in a more efficient, and at the end of the day, in a more cost-efficient way? Huh? I mean, this is at the end, it's always the euro which drives the system. So on this background, I have the great pleasure and the honor to introduce two very interesting and very, let's say, well-developed speakers. On one hand side is Charles Melchior from ERM Group. He will give us an update about LOHC transport from Scotland to Germany. We learned already in one of the, let's say, webinars in earlier this year about the option of LOHC. So he will give us an update about a project which is ongoing there. And then we have Dr. Jens Schmidt from TESS Company. He will present us another concept. He will present us the option of hydrogen transport using CO2 as a carrier molecule, which is at the end of the day, if you would like to interpret it on one way or the other, but this is what Jens Schmidt can do much better than I can do. It's also kind of LOHC because you also bound the hydrogen to a, let's say, to another molecule. So from that point of view, it's, let's say, two options, what we are tackling tonight, which, let's say, have the idea to come to another molecule which can be, in theory, more easily be transported. So this is the preliminaries, ladies and gentlemen, mesdames and messieurs. And with this, I would like to pass the floor to Charles Melchior from ERM Group. He will give us an update about the LOHC. So the floor is yours, Charles, and we are very much interested in your presentation. Please go ahead.
Yeah. I will first of all share my screen. Okay. Can find full screen mode. That's it. All right. Good evening, everyone. I'm very glad to be here to present one of our projects to you tonight. Thanks a lot to the Technical University of Hamburg for having me today. I will start my presentation with a brief introduction. So first of all, my name is Charles Melchior. I'm a partner at ERM and I'm based in Germany. For those of you who don't know ERM yet, maybe let me introduce briefly what we are doing so you get an idea with whom you are speaking tonight. ERM, that's basically the largest consultancy worldwide with a 100% focus on sustainability. We support our customers in a wide range of sectors with environmental, health, social, and risk-related services. And renewable is one of the sectors we are developing the fastest. We are particularly involved in the offshore wind on the hydrogen space, especially since our latest acquisition in that space with leading company like Element Energy, E4Tech, RCG, and also last year another company called Myron Space. We are not a traditional consulting company in that space, meaning we don't offer only strategic and technical services to our clients, but we are also a project developer ourselves. If you're attending one of the last webinars of TUHH, you might have heard of one of our projects in the UK called ERM Dolphin. That's basically the largest offshore project so far producing green hydrogen from floating wind. So that's something we are very active in. But today I'm here to speak about another project, which is called LHITS, on whose general aim is to demonstrate that hydrogen can be stored and transported at scale using liquid organic hydrogen carrier, or short LOHC. We are speaking here about a specific type of LOHC. I will come back to it later in the presentation. So the LOHC type we are targeting with this project is called methyl cyclohexane tolerant, short MCH. But again, that's something I will cover it later. The concrete objectives of our projects were twofold. First, we wanted to assess the EHS on techno-economic issues associated with two types of LOHCs, and we wanted also to compare them against other options for hydrogen transport by ship, namely ammonia, methanol, and liquid hydrogen. That was the first objective. The second one was to establish a basis for a pilot trial of LOHC shipment between Scotland and the port of Rotterdam. You might ask why Scotland and why LOHC? Well, several elements of answer here. First, we are we're very well established in Scotland. We are already involved in a few hydrogen projects there. I already mentioned ERM Dolphin, but there are also other projects we are part of, like a project off the coast of Aberdeen called Acorn. It's basically a blue hydrogen project producing hydrogen from steam methane reforming combined with a CCS project in the North Sea. Second reason is that Scotland wants to become a leading hydrogen exporter in the years to come. Under the Scottish government has very ambitious plans in that regard. They want to install up to 25 gigawatts of hydrogen capacity by 2045 in order to reach net zero. And of course, part of this hydrogen will be supplied to local off-takers and also off-takers in the rest of the UK. But not all of the hydrogen produced will be able to be consumed there. So it means that especially in the early years where hydrogen pipelines and infrastructure will not be established, Scotland will need a solution to export this extra hydrogen to other industrial centers. And here, of course, Scotland is looking at the furthest ones, which are located in Northwestern Europe. That's make the connection to the port of Rotterdam. You see on the next slide another view of our project, at least when it comes to the pilot trial we want to implement. On the right side, you can see all our project stakeholders. So as you can see, quite a diverse international consortium with a decisive support from the Scottish government. You see also one name of a company called Chiyoda, and Chiyoda basically will be the company as a technology provider we are working with for the project. Chiyoda is focusing on the particular type of LOHC called MCH, so the one I was referring to before. As mentioned before, the project intends to develop a pilot to demonstrate the feasibility of transporting hydrogen at scale from Scotland to Rotterdam. And here, for this trial, we will follow different steps. The first step will be the hydrogenation of LOHC at 2 terminals in the UK, St. Fergus and Sullenberg in the Shetland Islands. And for this, we'll use 2 different sources of hydrogen. Green hydrogen in the Shetland Islands, meaning produced from offshore wind, and blue hydrogen in St. Fergus, produced this time via steam methane reforming, and combined with the CCS project of the coast of Aberdeen. That's the project I already mentioned at the beginning, ACON, led by Storegga. And we are also supporting this project. The LOHC will be then shipped to the port of Rotterdam, where it will be released from its hydrogen part. And basically, the empty ships will return to the Scottish terminals, meaning with dehydrogenated LOHC, and then again, the loading process can start. Interesting here also is the fact that the shipment routes are not carved into stone, meaning some of the green H2 production. That's the basis we are looking at to start a trial, but we are also controlling all the routes. For instance, some of the green hydrogen production produced in the Shetland Islands could be also transported as LOHC to the mainland, up to St. Fergus, and from there be shipped to Rotterdam. But you have the general idea of the concept here. So that's the plan when it comes to the trial. I would like now to take a step back and briefly explain what we have done in the first phase of a project. We started actually with by evaluating the performance of different LOHCs, including ammonia, methanol, and liquid hydrogen, based on different environmental, health, and safety criteria. The objective here was to determine which of the LOHC options should be taken forward for more detailed assessment. And here our screening exercise revealed 2 options that were ahead of the others. First one, methyl cyclohexane toluene, so short MCH. On the other one, quite a difficult name to pronounce, perhydrodibenzyl toluene, short PDBT. These 2 options scored higher than the others on several parameters. I will come to more detailed results afterwards, but here, just to give you an idea, these 2 LOHC options can be stored in conventional fuel storage tanks, so meaning they can be handled as oil, basically. They can be treated also and handled at ambient temperature and pressure, which is a big advantage in terms of safety and also reduced cost. They are adapted to existing oil and gas jetty infrastructure, so existing infrastructure, I mean here. In terms of vessels, there is a lot of vessels of the type on size suitable for both MCH and PDBT that are already operating in the UK or could be repurposed with relative minor modifications. So that's also a big advantage of these options. On the next slide, you have a summary of the result of this EHS assessment. As was mentioned before, the LOHC materials were assessed based on different parameters. You see them on the right side. For instance, storage conditions, environmental harm, toxicity, flammability. On the chart, you see how our 2 pre-selected LOHC options, meaning MCH and PDBT, scored. Bit information here, the high score in this chart corresponds to a low risk applied to the parameters you see on the right side. So it means if you look at PDBT and MCH, which are the ones circled in red, they perform quite well in terms of toxicity and flammability, so both very low. Also in terms of their ability to be transported atmospheric temperature and pressure. So again, here I mean more safety. And they are also capable of using existing storage and loading facilities, which is also, of course, when you plan projects, a big advantage. That's for the EHS assessment part of our project. What we did next is also to perform a techno-economic assessment of the pre-selected options I mentioned, so MCH, PDBT, and also compare them once again against methanol, ammonia, and liquid hydrogen. We developed for this an energy model covering all these hydrogen carrier options, and we used an extensive set of parameters like techno readiness level, technical constraints, capex, opex for the equipment needed, etc., etc. We also modelize the transport of LOHC over different distances between 50 and 2,000 kilometers, and also based on different types and size of ships. Unfortunately, I cannot give you the details of the result we came to, since the study we performed is subject to confidentiality, but still the outcome of the exercise was quite clear. First, both MCH and PDBT as LOHC options are competitive to the other hydrogen carriers I mentioned. They're still also competitive over all the distances we have modeled. And secondly, and most importantly, I would say the levelized life cycle debris cost of both MCH and PDBT have the potential to drop well below 1.5 pounds per kilogram of hydrogen by 2030. So meaning the overall conclusion of the study is that LOHC is viable for transporting, storing, and delivering hydrogen between the UK and Northern Europe. That was the main conclusion we came to after the end of this techno-economic assessment. We are now busy working on a feasibility study that should precise the concept we want to implement for the trial pilot I was referring to in my introduction. And again, these trials should be implemented between Scotland and the Port of Rotterdam. You see on the slide all the work packages we are currently involved in. So a few examples. On the business case side, we are looking at the hydrogen supply to supply the two terminals I mentioned earlier, meaning St. Fergus and the Shetland Islands, with hydrogen. We are also in close contacts with potential off-takers in the Netherlands. We are assessing the concrete capex and OPEX needs for the trial. And maybe also on the more technical side, we are defining the type and scale of marine vessel that should be used for the trial, the frequency of shipments. We are also defining the storage requirements at the Scottish export terminals and also at the terminal of Rotterdam. We are assessing the potential for repurposing of existing facilities, oil and gas facility to LOHC. We are working on the EHS consenting roadmap for the project. And last but not least, we are coordinating very closely on engaging with internal and external stakeholders. Port of Rotterdam, of course, one of the most important ones in that regard. We are having very good discussions with them, and yeah, it's advancing quite well. In terms of schedule, as said, we started with techno-economic safety environmental assessment on the most promising solution for hydrogen transport using LOHC. So that was the first phase of our project. It was performed 2 years ago in 2021. We are now in the feasibility phase that I was mentioning. And we plan to be finished with this phase this year. Afterwards, what will come next will be a FEED study for the design of the hydrogenation plant at the Scottish terminals, and also the design of the release unit in Rotterdam to get back the hydrogen, and also a design of the storage system needed both on Scottish and Dutch side. And hopefully, if everything stays on track, we'll be able to launch the procurement on the construction phase for the pilot trial next year, so we can operate the pilot plant starting to 2025. Last slide on presentation is a kind of an outlook where what could come next. So again, we are focused right now on the pilot project to test the technical feasibility on economic feasibility of bringing hydrogen from Scotland to Western Europe using LOHC. But obviously, we are discussing also with other producers, with other ports. So the routes when it comes to LOHC transport from the UK to Northern Europe could be also extended to a later stage. So we are in discussion with the Port of Hamburg, Wilhelmshaven, others. So, and also in terms of producers, yeah. So there is a lot of potential in that regard to grow the opportunities around LOHC transport. That was it in a nutshell. If you have questions, I would be happy to answer them. Otherwise, back to you.
Yeah, thank you very much for this very interesting presentation, Charles. So I understood that, let's say, you are already quite concrete to transport the hydrogen from Scotland to mainland Europe and to find a smart solution for that. And let's come back maybe later with the discussion that, let's say, some comments from the chat are popping up. So let's discuss this after we have heard the presentation from Dr. Jens Schmidt from the TES company. And they are, let's say, following a different approach. So I understood that they would like to bound the hydrogen to a, let's say, CO2 molecule or to carbon and try to transport this one. So therefore, we are very much interested in your presentation, Jens, and we are happy to listen to your outline and to learn about your concept and your ideas. So the floor is yours.
Yes, thanks a lot. Jens Schmidt, Chief Technology Officer of TES, and my pleasure to present today. So I hope you can see my screen by now. Okay, perfect. So TES stands for Tree Energy Solutions, is a rather young company founded about 3 years ago. And the founders of the Tree Energy Solution company are very experienced and successful entrepreneurs in the oil and gas business for over 30 years. And so about 3-4 years ago, they decided that the future of energy is going to be in the green energy space. And they would basically set up a green energy company that produces and distributes globally green energy. If you look into the primary energy consumption, and this is a plot for Europe, 2019, so overall around 11,000 terawatt hours. And if you look into the split of these energy consumptions, you'll realize that a little less than a quarter is electrons, and the vast majority is molecules that are being consumed. And actually, if you would plot the same thing for Germany, the numbers would change. It's about 2,500 terawatt hours, but the split would pretty much look the same. So everywhere where we are in Europe, every country, it's pretty much a lot of molecules that are being consumed and only a fraction of electrons. Why am I showing this? This is important because the business model of TES is based on this. So what we basically believe in is that renewables should be enhanced and built and expanded as much as possible and as quick as possible all across Europe. But also the fact of the matter is, if you look into, for example, Germany, the existing renewables, wind and solar, just to offset exiting nuclear and coal, you almost have to triple or quadruple them. And pretty much the same is true for all the other countries in Europe. If you want to grow renewables, you should do that and you have to do it, but it's going to be difficult to exceed more than just the electron consumption. You would have to multiply it by a factor over what we have today to then tap into replacing all the molecules that are being imported. So with that in mind, TESS has started to decide, okay, we will need to import green energy. There's just no way we're going to have enough renewable electricity, land availability, and cost-wise to really offset all this primary energy demand that is today covered by molecules. If you want to do that, the basic concept is you go to places where renewables are easier to expand, where the production costs are lower, where land is more available. And so what you end up with is you go into the sun belt, the solar belt, which is basically Australia, Middle East, North Africa, the US, or you go to places where you have wind, or you go to places where you have hydropower. And best case, you can combine wind and solar to get a more even supply profile. It's very difficult to transport electricity. I mean, we all remember projects like Desertec, but if you want to run a wire from Australia to Germany or to Europe, good luck with that. So the easiest is to turn it into molecules. And that's where electrolysis of water comes in. So this is not a unique concept of TESS. Many companies look into this. You go to places where you can get renewable electricity, let's say for the cost of 10, 15 euros per megawatt hour. And then you turn it into green hydrogen by doing water electrolysis. And then the question comes, okay, now I have green hydrogen, very cost efficient because I have very low electricity cost. But how do I transport this green hydrogen from the place where I produce it to the place where the energy is needed? Let's say Europe or Germany for that matter. And we've just seen in the previous presentation that there's different approaches. Some people, I mean, transporting hydrogen per se by liquefying it is extremely energy intense. That's also what Professor Kaltschmidt mentioned in the opening. And the infrastructure, the ships and everything is not really ready. So people are looking for ways to transport hydrogen by derivatizing it or coupling it to other molecules and make this tiny little hydrogen molecule more transportable. LOHC was mentioned as an example. Others want to turn it into ammonia. So basically you take a nitrogen molecule and then you fuse the hydrogen and the nitrogen to make NH3, and that way you can liquefy and transport it. That was the original idea of TESS as well. So making synthetic green ammonia and then transport the ammonia. However, when we started to look into this with a lot of resources, time and money, one of our founders had a degree in agriculture and forestry. And he was basically asking the question, if Mother Nature had millions of years to build life on this planet, it certainly tried all different kinds of molecules and combinations. And yet today we are all running on a carbon cycle. Our human body is 98% carbon, oxygen, and hydrogen molecules. So basically, he said, can we look into using CO2? Can we use a carbon cycle to transport hydrogen? And the answer is quite simple. Yes, you can do that. Because if you combine CO2 and hydrogen in a Sabatier process, which Paul Sabatier investigated and got a Nobel Prize for 1912, so over 100 years ago, what you get is you take a molecule that is readily available and that is easy to handle. You take the green hydrogen, and when you merge those two, what you get is water, which you can split off and recycle into your water electrolyzer, and you get synthetic methane. So by doing this step, you're converting hydrogen and CO2 into a molecule that we know how to handle and how to transport for decades at a very large industrial scale around the world. Once you have combined CO2 and hydrogen to form synthetic methane, or how we call it ENG, like electric natural gas, then you can go into the existing infrastructure. If you build your electrolyzer and your methanizer in places like Australia, in the Middle East, in Abu Dhabi, in Qatar, in Oman, if you go to the US, you have an existing value chain and infrastructure for liquefaction, for example. So you can take an existing natural gas liquefaction plant. Natural gas is 90% methane plus a few other molecules, but you can also do pure methane. So you can feed it into the existing liquefaction. What you get is electric LNG or synthetic LNG, which you can put through the existing terminals on existing ships. The carriers are available. We've seen it on the press over the last months. And then you can transport your energy carrier using those ships into traditional gas import terminals. So once you have converted the hydrogen to methane, you've liquefied it, you put it on a ship, you can carry it around the world, very efficient. It's done on a daily basis lots of LNG carriers running around. And when you bring it into your LNG import hub, you basically have three options. The first one is you can convert it back into hydrogen. Most of the industrial hydrogen today, almost 90%, is produced from methane in steam reformers. So you can use the same technology. The only difference is instead of putting fossil methane in, fossil natural gas, what you're putting in is green gas that was synthetically produced from green hydrogen and CO2. And in this step, you basically do the reverse. So here you merge CO2 with hydrogen to make methane, and here you split the methane back into hydrogen and CO2. What we will do different is we will not use standard steam methane reformers. We'll basically use autothermal reformers with an almost 100% carbon capture. And that allows us to capture the CO2 in this reconversion, use the hydrogen at the destination, very cost efficient. And then you can use the cold of the incoming LNG to cool down your CO2. So you're serving two purposes. You're doing the regas of the cold LNG, make it gaseous again, and you're liquefying the CO2 at the same time, both without energy investments. The liquid CO2 you can put back on the ship and bring it back to the original place where it gets converted again with fresh hydrogen into methane. So you're creating a closed loop where the CO2 is not emitted, but is moved around like a glass bottle. In Europe, we have the system where you have glass bottles to bring around sodas, and then the bottle is always returned, filled again, and moves around. The second thing we can do is we can convert it back into green electrons. Gas-fired power plants are existing. What we would do is we would use an oxy-combustion gas-fired power plant, an Allen-Fedwet cycle. The reason being that you can easily separate all of the CO2 in that case. So you're burning your green gas with pure oxygen, which means you have no NOx emissions. You have a very pure stream of CO2 and water as the combustion product. Again, you can knock out the water, you can liquefy the CO2, bring it back in this cycle, and that way you have an emission-free, very cost-efficient cycle to move. Third thing we can do is, because the infrastructure for hydrogen is not ready yet, so when we first approached customers in Europe and specifically in Germany and explained to them why we can deliver hydrogen very cost-efficient, they said that's all great, but what we actually like is, since you have synthetic methane or ENG, why don't you give it to us through the existing gas grid? We can use it today. We can take it out anywhere in Germany, and we give you back the CO2 either by rail car, by barge, or we're going to build a CO2 infrastructure. So those are the three elements we can basically cater to. We can deliver hydrogen. We can deliver a climate neutral, known fossil energy carrier replaced by green energy, and we can produce green electrons on demand. If we look into this a little more detailed, so this is what we would call an upstream block. This is what we would build around the world in those areas where renewables are affordable. And you see the last auctions for solar. I think the very last one in Saudi was 1.04 cents per kilowatt hour, so 10 euros. Okay, that one has not been built, so let's stick to the ones that are up and running. There you are in the range of 13, 14 euros per megawatt hour. If you put that into your electrolyzer, the question is, electrolyzer is very capital intense. Do you only want to run it when the sun is shining, or do you want to run it at night? Then you need a battery. Same for your methanizer, your Sabatier process. Does it have a minimum turndown ratio? Do you need to keep it running at night? Then you need to either keep your electrolyzer running for hydrogen supply, or you need to store some hydrogen to keep it running at night. Luckily, we've been able to work with the key technology owners of these processes, and we've been able to find a process version that can be in hot standby. So you can completely follow the solar PV cycle. Same for the electrolyzers, which significantly reduces the need for battery, for example. CO2 being moved around, liquid storage, you regas it, you merge it with the hydrogen, you get your synthetic methane, you go into existing liquefactions, you use existing ships, you bring it into storage, and then you can do the three different things I explained. In terms of shipping, because I understand part of this webinar is also about transportation, the business model has been built basically on independent ships. So you have one LNG carrier that brings the LNG, and you have a CO2 carrier that brings the CO2 back. What we as TESS are doing is we have designed the complete multi-gas carrier that can carry both. So basically, we've designed a ship, we've selected the material, we've cryo-tested it through 300 cycles, which is worth 30 years of transportation. Everything's been ready to order. where you can transport LNG at minus 163 degrees and 1 bar, and the same ship can take the liquid CO2 at 8 bars and minus 50. The beauty is at those conditions, the density of liquid CO2 is exactly high enough that all the carbon atoms that come as CH4 can be transported back as CO2. So you can basically close the loop with the same ship. And since the ship has to go back anyway to pick up the next cargo of CH4, putting it with CO2 on the way back means very, very low transportation cost in addition. So that's the cycle. This is the upstream block. We will place multiple of these in regions like Australia, Middle East, North Africa, and the US. And then we have the downstream blocks, which is basically the import hubs with the energy park behind it, where you do the conversion into power, into hydrogen again, or where you just distribute the e-gas and get the CO2 back. This is one of the first of these import hubs we are building in Wilhelmshaven in Germany since 2019. So what you see here is a schematic. The first part is a more or less traditional LNG import terminal, because all it does is it takes liquefied synthetic methane, which technically is the same like LNG. So you'll have the same storage tanks, you're going to have the same regas, you're going to have all the same setup. What you see here behind this, and we bought 145 hectares. So the terminal is going to be, let's say, around 30 hectares. The rest is then for the back conversion into hydrogen, into green power, for the liquefaction of the CO2. You see a lot of CO2 storage tanks here. And we're also going to put local electrolyzers to utilize excess wind power, and then use the oxygen byproduct in the autothermal reformers. So we've developed this for the last 3 years. Of course, now we have significantly accelerated this due to the energy crisis, and the German government was kind enough to add us to their acceleration law. So this project has now full support from the German government. As a consequence, what you'll see is the original plan was to start the terminal up in 25-26 to be able to import this synthetic green gas. We've accelerated that now. And then in addition, the government has asked us to put a floating storage and regas unit that will even start up this year. So technically, with our way to convert CO2 and hydrogen into synthetic methane, even a traditional fossil gas floating storage and regas unit can be used to bring in our synthetic ENG. In 2026, we're also going to start to export CO2 so we can start to close the loop. And then till 2043, we will basically replace all the excess capacity that is initially going to be used by third parties to bring in fossil LNG to be completely turned into green ENG. So again, this is the cycle that we're using. And if we look into the different technologies employed, one of the key questions is, okay, is this technology ready for prime time? Can you actually make synthetic natural gas at that scale? And the answer is yes. There's multiple gigawatt scale synthetic natural gas plants operational around the world. So basically using the Sabatier reaction, the only difference is that in these plants, it's usually coming from a coal gasification, for example, so you have syngas. So instead of pure CO2, you have a mixture of carbon monoxide and carbon dioxide. So what we're going to do is slightly different, but if you talk to the technology suppliers like Topsoe, like MAN, like Johnson Matthey, and a few others, they basically have tested this with the same catalyst. They have tested the heat release. It's actually easier to manage because the reaction is less aggressive, so you need less recycle to control the temperature. You're forming a little bit more water if you go with pure CO2, but that can be knocked out between the individual reactor stages. And basically, they are ready to give a full commercial warranty on a plant of a gigawatt scale to do this synthetic ENG. The water that is formed in the reaction can be recycled. And one of the reasons many people said, well, why does this make sense? Because if I look into the reaction, what I get is I'm reacting CO2 with precious hydrogen, and half of my hydrogen goes into water. How can this be efficient if I lose 50%? Well, on a mass balance, that is correct. 8 kilograms of hydrogen produce 16 kilograms of CH4, and basically half of my hydrogen goes to water. However, if I do an energy balance, so if I look at 8 kilograms of hydrogen and now I use lower heating value, that means I put 960 megajoule in, and what I get out is 800 megajoule worth in my CH4. So on an energy basis, on a lower heating value, I'm 83.3% efficient. The rest of the process is waste heat that is rejected at very high temperatures. And I can, for example, use that steam to make additional power, or I can even feed it into a high temperature electrolyzer, easily bringing the overall efficiency up further. And what's important is when I import my green ENG, my CH4, I can use this energy not only to relieve the hydrogen that is bound to the carbon atom, but also split additional water. And that's why we get a lot more hydrogen out than you would think just based on this. So the overall efficiency is well above 90%. All the individual units in this cycle are readily available on industrial scale. So we've worked with Technip to put together the overall cycle. This slide is slightly outdated. We have 14 electrolyzer suppliers that we've worked with to get their packages. For the Sabatier, for the methanization, we've worked with these 3 companies. For the oxycombustion power plant, we work with Net Power, where we sponsored their last test run in La Porte, 50 megawatt pilot plant, demonstrating all the way to grid synchronization and power injection. The reforming back to hydrogen, we have different packages from different suppliers. The whole terminal and regas is standard equipment. So this is something that every LNG terminal has. And CO2 liquefaction, we're also working with some of the market leaders. So the beauty is you're piggybacking on an existing infrastructure that has been built with billions of dollars, and you can reuse it. You can even blend slowly. You can start in a liquefaction that runs on entirely fossil natural gas today. You can build your first electrolyzer and you can blend in 5%, 10%, 15%. And you can basically increase the share of green gas till you have completely replaced your fossil gas. And the same liquefaction, the same ships, everything can still be used, but now is running on a completely green energy cycle. Efficiencies. If you compare the different carriers, that's always one of the first questions. Ammonia, LOHC, liquefaction. What is the efficiency around the cycle? Well, we will all share the same renewable power cost, whether it's an ammonia plant or an LOHC carrier. The electrolyzer is going to be placed in those regions. We all have the same renewable power cost, let's say 10 to 30 euros. We will also all share the same electrolyzer efficiency. Yes, you can choose different technologies, but everybody's going to have access to the same basis of technology. So let's assume on average, we have a 72% efficiency of our hydrogen production. As just shown, the Sabatier, the conversion to CH4 is at least 85% efficient. If you do a bit of heat integration, you can certainly bring this up. That's certainly one of my big jobs, is to increase the overall efficiency. But off the shelf, buying standard equipment, you have about 85%. Liquefaction depends a bit on whether you use an old existing one or you build a new one, but overall around 91 to 96% efficient. Then you have a synthetic liquefied CH4, which you can put on a ship. And there you basically have, for transportation from, let's say, Middle East through the Suez Canal to Germany, you have a 96% efficiency. 4% is basically your boil-off gas that you use during transportation to propel the engine. So of course, our ships will run on the ENG. They will actually run on an oxycombustion ENG engine that we've developed and are currently testing in the lab with exhaust gas recycle to make sure that we capture all the CO2 and put it back in the cycle. So it's going to be emission-free. When you arrive with your cold gas, you have to regas it. And that's where the integration with liquefying the CO2 helps, because I don't need to inject any additional energy. I don't have to burn gas to create the heat to regas it. I can basically use my CO2 that needs to be liquefied to do the regasification, and that also then dramatically reduces the energy need for liquefying. Then it becomes interesting if I have a customer who wants, for example, only a climate neutral energy carrier. That customer can easily take the ENG and he doesn't have to convert it back to hydrogen. That means the total efficiency is going to be around 74 to 78%. If I include my electrolyzer, it's around 53 to 56%. Easy numbers, 50% efficiency means my variable cost will be twice the power cost. So if I go in with 20 euros per megawatt hour, by the time I arrive, I'm at 40. And then, of course, plus the capex for running the whole thing. If I want hydrogen, I can convert it back in a reformer. Efficiency is also in a range of 80%. I can use the waste heat for other things. But then I have a total efficiency of around 58 to 62. And if I include my original hydrogen production, I'm a little less than 50%. So that cycle is existing, all the technologies are there, and it allows you to transport at an efficiency that is very close to all the other solutions, your ENG. We did a life cycle analysis. If you don't do any offsets, no additional capture, you get to a 93% lower footprint. So this only has 7% footprint of a normal fossil natural gas. And we can add, for example, to bring it to net zero, we can add direct air capture. Yes, it's expensive, but we only need to capture a very small fraction of the overall cycle. So if we share the cost for that, it only adds about €2.30 per megawatt hour. And then you're at true net zero. Cost comparison, of course, it all depends on your assumptions, but if we put in €20 per megawatt hour for PPA, we basically say the cost that we get to, including the CO2 capture and return at the customer, is around 100. We ran the same analysis for ammonia with a Haber-Bosch cycle, which is also a bit less flexible in terms of following the renewables. We looked at ammonia market price, we looked at TTF. So what we can do today is we can basically easily beat TTF, and okay, now it's gone down a little bit again, but if you add TTF plus the emission cost, because this is already climate neutral, we're getting to very interesting territories. If you now reduce the PPA price, or you go to the US and put the IRA benefits on top, then you come to extremely cost-efficient solutions. Pros of e-gas, non-toxic. Everybody knows how to handle LNG and gas. Can be directly used by the customers, no change of the process, so no costly shutdown, retrofitting turbines, replacing burners. You can use the existing natural gas infrastructure, so we don't have to wait for the backbone. There is no technology risk, as all these things are available, and the production costs are lower. And since the volumetric energy density is higher, to transport the same lower heating value as ammonia, you would need 1.7 times the ships. And the outlook, if we bring the renewables back to below 10, electrolyzer capex drops to 250, as many project, and further efficiency gains, we can certainly get to range like 35 to 40 euros per megawatt hour, including the CO2. So we can offer clean and green hydrogen, green gas, green power, and of course, in the interims, we can take hard to abate CO2 and inject it into our cycle and turn it back into useful fuel. And all these are flexible between the different outlets. So the value proposition is we can produce green hydrogen with renewable energy, solar, wind, and hydro. We can combine that, and we can basically guarantee 100% CO2-free circular product with no technical risks. And you can diversify supply because you can build around the world in all the places where renewables are there, and we can start industrial scale. So we don't need to wait for any technology developments. We don't need to wait for the first large ammonia cracker. We don't need to wait for hydrogen pipelines. We can just keep going. These are the places we're currently looking at. US, due to IRA, is now highest priority. We're also looking into Saudi Arabia, UAE, Oman, Egypt, and Australia. One of our partners is Fortescue Future Industries, just added 130 million into the company and to the import terminal in Wilhelmshaven. We also have E.ON on board. We have HSBC and UniCredit. And basically, we're going to develop places in all these regions, and we're also going to add more import hubs. With that, I'll open it up for questions.
Yeah, Jens, thank you very much for this very interesting presentation. And also thank you very much again to Charles for his presentation. And now, ladies and gentlemen, we have seen that there are two different concepts. On one hand side, you use CO2 as a molecule, as a carrier molecule, and the other hand side, you use a, let's say, carrier molecule, which is a, let's say, organic molecule. And the question is, we have learned from Jens about the advantages from CO2. We have learned from Charles about the advantages from his molecule. But I understood that the project, what you present us, Charles, has been not such a long transport distance compared to what Jens has presented. Is this an advantage when you go for liquid organic hydrogen carrier, these organic molecules, if you don't have so long distances?
So that's true. So the focus of the project is definitely on shorter distances. So we were talking about so the distance between Scotland and Rotterdam. So it's not the plan. The plan is not to go to Australia and other countries we just discussed. Still, when we did our techno-economic assessment and where we looked at different distances, I was mentioning, I think 50 kilometers to 2,000 kilometers. The result of our assessment was to show that even at larger distances, LOHC remained competitive to other hydrogen carriers. Still, we decided to look at the North Sea because that's where the opportunity is. But longer distances, that's something we would investigate maybe later on. But yeah, at least the result of our assessment is there is here competitiveness also between these energy carriers.
Because the next question would be, if you go for longer distances, then you still think that, let's say, your carrier is better, or the other way around to Jens, if you go for shorter distances, that you go, for example, for wind also from Scotland, is then still the CO2 loop and the LNG transportation the best solution, or you think that the very best or the most economic and most promising solution depends on the distance? I mean, my initial, just to make one more comment, Charles, my initial idea was, when you talk about Scotland, I mean, you have a lot of gas pipelines, so why you don't transport the hydrogen not directly via a gas pipeline, which is from Scotland? I mean, this would be at least a sound technical solution.
Yeah. I mean, what we are working on is a pilot trial. That's for sure. If we compare LOHC to a transport by pipeline, it's a completely different story. Yeah? The thing is, in order to export right now, the excess of hydrogen that will come in the next years in Scotland, you cannot wait for the European backbone to be further developed also in the North Sea. So we see it like really as an opportunity to test also the LOHC transport, given the opportunity you have in the North Sea. But I completely agree with you. Once the European backbone is here, on the hydrogen pipelines are there, it's something we should to assess again what's the best solution to go for. On obviously, hydrogen pipelines have a big advantage in terms of costs here.
Yeah, I would add from our perspective, obviously we look into setting up production hubs where we have renewables at very affordable cost, and that is by definition quite a distance to Germany. So short distance transport is not something that we looked into. I would also say the main advantage of going this CO2 hydrogen to synthetic ENG is not because of the transportation. Yes, you have an existing infrastructure, you have existing liquefactions and ships that can do this. But really the main benefit is that it's very efficient to do it, and that it gives the customer a chance to start today, because he can use something that is well known. If you're running on natural gas today, you can switch to green ENG without any modifications. And if the hydrogen backbone is ready in 5 years, in 10 years, then we can always do the conversion back to hydrogen at the receiving port and inject it into the grid. So for us, the methanization and the liquefaction and transport by ship allows a very efficient long distance transport. And that's really the key to enable the big differential between the renewable energy cost, which is ultimately the business model. You go to places where you pay less than half for the renewables, and that way you can transport it.
Yes, thank you very much for that. I mean, the crucial point for both concepts is where come the LOHC, the carrier molecule, or where comes the CO2 comes from. Yeah. So, I mean, this is my interpretation, Charles, please correct me. I would assume that your molecule comes from crude oil, right? Is it a green molecule?
To tell you the truth, I'm something, I'm not an expert in the project, so it's something that I could definitely check with my colleagues and come back to you on that. I mean, we are looking at the MCH option, whether it's organic or based on oil. I don't know to say. Yeah.
Yeah, for us, it's very straightforward. We have 3 options. First of all, it's a closed loop. So we only need to fill it initially, and then we only need to top up the small losses that happen. We can top up the initial loop with biogenic CO2. So we're in the process of securing that, and then we can build this loop. The second option, we will have a lot of waste heat available at the production side with the methanization, and also at the receiving side with the reformers. And that is, of course, a significant contributor to reduce the cost of direct air capture. If you look into direct air capture today, the cost is mostly the energy it takes to regenerate the solvent. We have that energy available at the right temperature level, so we can easily bring down the cost of direct air capture and then top up or even fill our cycle with CO2 from that. And the third one is we will have plenty of unavoidable CO2 emissions. Let's look at the cement industry, for example, and they would be more than happy to do our initial filling of the cycle. But as again, we're going to create a closed CO2 loop. So it's only where you get it initially from, and then you have 2-3% loss in the cycle, and those will be topped up by biogenic or by direct air capture.
I mean, this is also the point which has kind of just popped up in the chat, you know, that they say not every end user, this is what they say here, not every end user of the gas may have the ability to capture the CO2. But I mean, I understood from your concept that you said, okay, you can basically put this into the natural gas grid, and then you can sell it to basically everybody. You can sell it for the mobility sector, for CNG vehicles. You can sell it to, let's say, to the household customer for the condensing boiler to provide heat and electricity. And then it's getting a little bit challenging, you know, to collect all the CO2. And
yeah,
then,
you will not be able to collect it all back. And that's also not the primary focus right now. I mean, we're obviously interested in industrial off-takers like direct iron reduction plants that already have a carbon capture part in there. And they will capture 85, 90+ % of the CO2. And then our job is to top up the remaining part. And we have to do that for two reasons. One, we have to reach true net zero. So whatever is lost at the customer, we have to do either direct air capture or bring it in as biogenic CO2 to make it true net zero. And even if we were not interested, which we of course are as a green energy company, we want to be true net zero, but we physically need the carbon atom back so that we can fuse it as CO2 with the next hydrogen to make synthetic methane to transport again. So we will always have to provide the equivalent of the carbon atoms that leave the liquefaction as CH4 somehow need to come back to fuse again with new hydrogen.
okay, I mean, the point is what you said, okay, biogenic carbon, this is what I do understand. I mean, according to what we, let's say, understood, or what I understood personally so far, is when we go for direct air capture, I mean, you need lots of energy and you need a lot of apparatus, you know, big, let's say, areas and surfaces to, let's say, catch the 400 ppm or 420 ppm, which is in the air. And this is, at the end of the day, from a, let's say, technological point, quite demanding. How do you see it if you would, let's say, just go for direct air capture, as let's say, people here in Germany or in some other areas would like to see it because they are not so happy with biogenic CO2? Yeah.
So first of all, biogenic CO2, in my view, and it's my personal view, but I think we as a company have the same view. Biogenic CO2 is going to become very scarce because there's going to be a lot of people that go after it. If you were producing synthetic aviation fuel, for example, there's no way you're going to capture at the emission point at the plane. So they will have to find these kind of solutions, and there's going to be an increasing demand and price attached to biogenic CO2. So for us, if we can secure it for the initial fill, great. If we cannot, then we have to do direct air capture. On direct air capture, we're of course working with a lot of established, all the usual suspects, whether it's Climeworks or Carbon Engineering, all those guys that have different processes out there. We are also working with some very promising startups. And right now, one of our partners has a trial run in Australia where they already reach capture cost of less than 100 euros per ton. And that is including providing the energy from renewables. If we add on top that we have the waste heat to do the regeneration pretty much for free, then we bring those costs down further. And yes, there's a lot of interesting developments, and we think that it will be technically possible to capture at a very attractive cost in doing direct air capture. Nevertheless, a point source is always going to be an easier way. So when we build, for example, our autothermal reformers at the receiving hub, once the hydrogen infrastructure is ready, we can capture 98% of the CO2 easily as part of that ATR. Same with the oxy-combustion power plant. 98% CO2 retrieval rate is basis of the engineering package we have. And then you only need to top up 2%, which means the cost of your direct air capture is diluted by a factor of 50 if you put it on the whole cycle.
Thank you very much for that. Let's come slowly to the end of our webinar tonight. Maybe just look, let's say 10 years ahead, yeah, till the early 30s. Yeah? And let's assume that politics takes it serious with climate protection and with the reduction of greenhouse gas emissions. And let's assume that, such a, global hydrogen market will emerge. How do you see the share of, liquid organic hydrogen carrier in, 10 years time? And how you see the share of CO2 or natural gas, or however you call this in nice words. Sorry for being unpolite, in the next years. Maybe what is your expectation related to the market development, Charles? And what is your expectation, Jens, from this point of view in the next, decade?
Mm-hmm. So first of all, don't think there is a real competition between all these hydrogen carriers, or to put it in other ways, there is space for all of them, because in the end, it really comes to the project, there's project specificities, what is available. So we were discussing, I think both of us, the possibility to reuse existing facilities, existing vessels, but from project to the other, it might be different. That's the first step. Also, I think a distance also play a role on, also obviously the emergence of the European backbone. Also, that's something you should consider to evaluate the potential of each options. Having said that, it's really difficult for me to give you a concrete number how much market share LOHC could get in the near future, but definitely whenever, for very, I would say, short distance where hydrogen pipelines are not available, I think LOHC does have a big role to play.
Yeah, I would first of all support and echo that comment. If I would have one wish, I would like to stop this. One solution is good and all the others are bad. That seems to be the approach of the century, whatever. But there's going to be a need for green ammonia in the fertilizer industry. There's going to be a need for LOHC to transport pure hydrogen when you need the hydrogen again. There's going to be maybe even need for liquefied hydrogen short distance. And there's certainly going to be a need for ENG, electric natural gas, or synthetic natural gas, because it depends on the end user and what he wants to do it. And if you are today producing fertilizers, you'll never buy our ENG, you'll never buy hydrogen from an LOHC transportation chain. You'll always directly produce the ammonia at the source of the hydrogen. If you are using natural gas today, there's a good chance you'll stick to ENG if you can get it climate neutral. Why would you not? So I think there's going to be a big play. And if you look at the order of magnitude of the problem we have to solve, if TES is successful in implementing the import hub, and we're already building it, so that's going to happen. If we want to fill this Wilhelmshaven terminal, we're going to invest over 100 gigawatts of electrolyzer capacity globally, and we're going to have 250 terawatt hours of green energy to import. That is just 10% of Germany's primary energy demand. So there's place for 10 other TESs just to supply Germany. And whether they use ammonia or ENG or LOHC-based hydrogen doesn't matter. And then if you want to do it for Europe, we need 40 TESs. So the challenge at hand is so big, the market is so huge, that we are not worried about competition at all. Let's get something going. We have something that is economically viable, and it's important we start today.
So maybe then this was a misunderstanding. This is not what I would like to say, one or the other. I mean, I also said in one of the former, let's say, webinars, that I believe that the world become more colorful, and that we will see not only one solution, we will see quite a lot of solutions. Because as you said, I mean, when we go for ammonia, then if we can use it as ammonia, then it's the most promising solution. And what I also said a couple of weeks ago is, when, for example, Airbus will fly with liquid hydrogen, then the best way is to transport the liquid hydrogen, because then you have the energy demand to liquefy it there where the energy is cheap. Yeah. So therefore, it's not one or the other. It's additionally, but nevertheless, I mean, my idea, my question, or my question was how you see the market share. And I understood from you, Jens, that you said basically, well, we need 40, 50 more TES to, let's say, provide energy in Europe. So that means that you have a share of, let's say, 2%, 5% or something like this related to primary energy. And from you, Charles, I understood that you said, okay, for shorter distances, you will see a certain market for LOHCs, and then it's a couple of percent. Is this right or is it wrong? Kill me if I'm wrong.
No, if we get 10% of the German primary energy market, that's going to keep us busy for a while to build all the electrolyzers. And of course, we have ambitious goals. And Germany and Europe is not the only market. And to be also very fair, I mean, there's a lot of regulatory work to be done in Germany. If I compare that to the Asian market, Japan, Korea, they are ready to import ENG today. They actually do it. So I think Europe has to be careful that with all these discussions, the US made a huge step now with the IRA. Everybody's rushing to build something over there, and other markets are opening up for all these different carriers and all these different pathways. And we need to be careful that we are not getting lost in, is it biogenic? Does it have to be DAC? And in the long run, it all needs to be clean and climate neutral, but let's not try to prevent these solutions by being overly restrictive in the beginning.
Okay, so maybe the last round, and then we terminate, even to the fact that I'm not a Terminator, I'm not Arnold Schwarzenegger, for sure not. But nevertheless, I mean, what do you think is needed to, let's say, help you to develop the market, the transport market for LOHC, Charles, and for, let's say, green methane? Yes. What do you need in a nutshell?
So for us, it's easy. I can go first. The infrastructure exists to distribute the ENG today. We can import it. We can put it into the gas grid. So once the hydrogen gas grid is ready, we can also do that. But what is essential to get the cycle going is two things. One is we need a way to get the CO2 back. And that can be done initially by rail cars or by barge. But in the long run, it would be good to have a pipeline network for that. And the second part is more a regulatory topic. Of course, if a customer uses our ENG, captures the CO2 and gives it back to us, he should not be required to pay an ETS emission certificate because the CO2 is never emitted. So regulatory, this needs to be accepted that a carbon capture and use cycle is credited against the emission certificates. If that's a given, then we are good to go. Okay, Charles.
Yeah. We'd have a slightly similar answer when it comes to LOHC. So obviously LOHC it's an emerging market, so there is a lot to be done, especially to lower the cost. So political support is needed for sure. Clarity on the regulatory framework for sure as well. Having said that, as for CO2, when it comes to infrastructure, when it comes to the ships, to the facilities, we can also reuse them directly with LOHC. So to answer your questions, it's more on the political support side, meaning framework and also funding. Yeah, funding is needed, but we'll need help to develop. Yeah.
Okay, was this? Gentlemen, in this case, I think we will finalize our webinar for tonight. So first of all, I would, of course, thank the two presenters, Charles Melchior and Jens Schmidt, for giving this presentation and for being available for this controversial discussion, or at least a little bit controversial. So I want not to be too controversial, but at least a little bit. So thank you very, very much for that. Thanks very much for your presentation, for your time, and for the fact that you presented here your view. And then I would like to thank also the participants in this webinar for being here and to listening to our presentations. And then last but not least, I would like to thank again the organizer, and especially Felix Mendler and Wolfram Tuschewitsky, for getting this everything organized from a organizatorial and from a management point of view, and of course the translator for translating this, at least my bad German English and your good English, into nice French, which is hopefully understandable to our French-speaking community. And last but not least, of course, I would like to thank Shoke Aslush, as well as our Tunisian colleagues, as well as GIZ for sponsoring the translation. And with this, I wish everybody a nice evening. And before I finalize, I'm still not finished. Yeah, before I finalize, I just would like to mention that next week, same place, same time, we will have a presentation from Linde about technology advances in the field of liquid hydrogen, and another presentation about interchangeability of hydrogen injection in gas pipelines, which is also quite interesting, quite promising. And then the week after, we have a presentation which goes more in the organizational point of view. On one hand side, a hydrogen guarantee of origin, and hopefully, most likely also a presentation from, let's say, the implementation of hydrogen at the, let's say, energy markets, how this can be realized. And then we will have, hopefully, if everything works out, then some more presentations, a country report from New Zealand, a country report from the US, and hopefully also some country reports from the Middle East. And then after this has been then finalized, we will also finalize for this winter term, this webinar. So still there are some interesting, challenging, and quite, let's say, actual activities and topics to come up. And with this, Mesdames et Messieurs, Senores et Senoritas, ladies and gentlemen, meine Damen, meine Herren, I wish everybody a beautiful evening. Don't work too hard, enjoy yourself, and let's say, have a beautiful evening, and see you next week, same place, same time. Bye-bye.